difficult 6-digit version of this problem, SMO Junior, and I forgot to write down, I think it's round 2. It tends to be more geometry, I think. Okay. Now, what we're trying to do here is, it's a question, just a yes or no question. Are there any 4-digit square integers such that the integer formed by the first 2 digits is one more than the integer formed by the last 2 digits? Okay. Now again, this turns out to be substantially easier than the problem that was 6 digits that was presented not too long ago at Cocoa Education. Now, if we let y be the integer formed by the last 2 digits, okay, that would place y in this position. This would be the last 2 digits, okay? And then it's one more, the first 2 digits. So that's why we have to put y plus 1 in the first 2 digits would mean you have to be multiplying by 100 if you just think of a 4-digit number, okay? 4-digit number, that would require 100 to push it over 2 places, okay? Now, so when you simplify this expression, you get something pretty easy. And 101 is a prime number, which turns out to make this problem substantially easier. Now, so we're going to go ahead and assume that n is a square integer. Of course, k is an integer, and see where this leads us. Now, this is just some straightforward algebra here that leads to the difference of 2 squares. Now, notice that something that's quite important here is k has to be less than or equal to 99. And you guys may have surmised why that's true already. It's a 4-digit number, right? N has to be a 4-digit number. So if just 100 squared is 5 digits, right? That's equal to 5 digits. It's 1 followed by 4 zeros, right? So it's kind of useful to have this upper bound. Again, this is 5 digits right here. Okay, we have an upper bound of 99, and the lower bound, I think, is actually 32. 30, you computer programmers, 32 squared is the same as 2 to the 10th, which is 1,024. Okay, so anyway, right here, what we get is a circumstance where you have 101, which is prime. It doesn't take long to verify that. Check for 2, check for 3, check for 5, check for 7. And that's it, because all you have to do is check up to the square root of 101, right? Okay, so 101 is a prime number. That means it has to divide one of these, okay? Now notice that and it not only does it have to divide it, it has to be equal because of this restriction, k less than or equal to 99, right? Okay, so what we have right here, 101 cannot equal to k minus 10, right? Let me just write that down. If 101 was equal to k minus 10, obviously that would give us a k bigger than 99, right? That would give us a k bigger than, namely 111, right? Now, if we set 101 equal to this first factor, okay, that implies that k is equal to 91. Okay. And so, let's see, what do we have right here? We have 101 on the left-hand side. And so you can see what this would imply. This 101 would cancel with this 101. And this would all imply that y is equal to, again, y'all, in the name of saving just a little bit of space right here. This is 101. The 101 had to be assigned to this factor. It couldn't be assigned to this factor, all right, because of this this upper bound. Okay, so this will cancel out, and if you put 101 into here, you get 91. Excuse me. If you put the 101s cancel, and what does that leave for this right here? What does that leave for this value right here? This would be 91, right? And so you would have y, let me just write this. We have y right here. This 101 cancels with the 101 that would appear right here. And so you would have y is equal to 91 minus 10, which is 81. Sorry about that. Took me a while to get that out. Is that clear, folks? Again, 101 has to be assigned to this factor, which means that k is equal to 91. But 91 minus 10 is 81. Okay? And so what we get right here is 100 times 82, right? 100 times 82 plus 81. See, and there's a difference here. So what is this equal to, my friends? This is equal to 8200. This is equal to 8281. So, and I think this is the only one. This is the only 4-digit perfect square. And notice this is equal to 91 squared just by construction. Okay, notice you didn't have to do that calculation directly. The construction gives it to you. Okay, it's not too hard to do that in your head, but it just comes to us naturally. It just kind of falls out of the problem. So this is our answer. And again, let's confirm 82 is one more than 81, which is exactly what this says. It's one more, right? So are there any? The answer is yes. And the answer is 82, 81. And I'm very sure what we've shown is that this is the only one. And that's the answer to the question. But for any doubters, again, what is it? 91 squared? It's equal to 91 squared. Okay, folks. That is it. I think there was like 5 if you allowed for 6 digits. It was a lot more complex. You had to use maybe the Chinese remainder theorem or something to get it all sorted out. But this one was actually quite simple in the sense that it's a forced circumstance here, mainly because of this upper bound, that you have with just 4 digits to work with. So there's only one 4-digit square with this so-called special property. All right, that does it. Okay, thanks for viewing.